Hi folks, we're going to be doing a quick tutorial today on how to draw Lewis structures, and we are going to use a stepwise method. There are 5 steps we're going to follow. We have step 1, which is you take your structure that you have and you add up all the valence electrons. The valence electrons you can get based on the position of the atom in the periodic table, and you have to add +1 electron for every negative charge and subtract 1 electron for every positive charge. Then we go to step 2. Step 2 is to draw out the structure, and by drawing out the structure, what you're going to be doing is connecting all of the atoms with single bonds. And typically, if you have a compound, the first element that's listed, so if you have something like CO2 or SF4, typically the first listed element is the central atom. That is not true if the first element is hydrogen, because hydrogen can never be a central atom. Once you've done that, what you do is you take the electrons that we counted up in step 1 and you add electrons to the outer so the outer atoms. And what you want to do is add enough electrons to fill all of their octets. So we're going to fill the octets of outer atoms. And once you've finished that, you check to see if you used all your electrons that you counted in step 1. If you have any additional electrons left over, we go to step 4, which is put them on the central atom. Okay. Then what you do is you check to see if all of your atoms have a full octet. And if they do not, what you want to do is see if there's an opportunity to take an electron pair on an adjacent atom and make a multiple bond. And this sounds complicated when I just say it out, but I'm going to show you some examples, and hopefully that makes it a little more clear. So we're going to make multiple bonds. I guess we have more than 5 steps. I mean, the next step, what we would want to do is check formal charges. And the formal charge is a charge that each atom has, which is based on the number of valence electrons that atom would normally have. Subtract the number of bonds. Subtract the number of unshared electrons. So what that means is a lone pair would count as 2 unshared electrons. Once you have this, you should be done, and then you can do things like assign the shape. You can assign the hybridization as well. And what you can see that I've added here on the left-hand side of the screen is a table which you can then use. You can apply this to figure out the bond angles, figure out the shapes, figure out the hybridization. All of these things can be figured out directly from the completed Lewis structure that we'll have by the end of this process. Wonderful. So, without any further ado, let's start with some examples. And so we're going to start easy. The first example that I want to look at is going to be methane, Ch4. Okay. So our first thing that we want to do is count up all of the electrons, all the valence electrons in Ch4. So what we're going to do is bring up a periodic table. And we're going to, first of all, locate the elements. So we have carbon and we have hydrogen. The valence electrons you get based on its position in the periodic table, where everything in the first column has 1, second column has 2, 3, 4, 5, 6, 7, 8. So based on where carbon is, carbon should have 4 valence electrons, and each hydrogen should have 1 valence electron. If you remember that, we're going to have 4 valence electrons for the carbon plus 1 valence electron for the hydrogen times 4 because we have 4 hydrogens and that gives us a total of 8 valence electrons. So that's step 1. Step 2, if you remember, what we want to do for step 2 is then draw out the structure with the first listed element as the central atom. So that's going to be our carbon. We connect it to all the other atoms with single bonds, like that. And what we then need to do is, once we've connected it, we count up the electrons that we've used to make all of those single bonds. Each single bond is a pair of electrons, so each counts as 2. We have 4 single bonds, so the 4 single bonds times 2 electrons per single bond is 8 electrons that we've used up. If you look at the result from step 1, we only had 8 valence electrons to begin with, so we used all of them, all 8, to make those 4 single bonds in methane. So that means we have no additional electrons. We can't do the next step. We can't do anything beyond this. So what we would want to do, just to make sure that our structure is as good as it can be, is we want to count the number of valence electrons, make sure that everything has a full octet. So carbon, to have a full octet, needs 8 electrons around it. It has 4 bonds. You can see there's 1, 2, 3, 4. So those 4 bonds each have 2 electrons, which makes a total of 8. So there are 8 electrons around the carbon. So it has an octet, it's happy. The hydrogens, they only need 2 electrons each to fill its outer shell, because it's in the first row of the periodic table. And they all have 2 electrons because they all have 1 bond as well. So everything has a full outer shell, so that means our structure should be good. I guess the next step, what we want to do is determine formal charges. So for formal charge, if you remember, what we want to do is, let's start with the carbon. We take the number of valence electrons that a normal carbon atom would have, which is 4. Subtract the number of bonds. It has 4 single bonds. Subtract 4. And then you would subtract the number of unshared electrons. And there's no lone pairs on the carbon, there's no unshared electrons, so that number is 0, and that gives us a total of 0. So the formal charge on the carbon in methane is 0. The hydrogen, you can see as well, it has 1 valence electron under normal circumstances. It has 1 bond that it's making, so you subtract 1, and it has no unshared electrons around it, so you subtract 0, which is 0. No formal charge on the hydrogen. We're done. We have the correct structure. We have completed all the steps. And what we can do is go over to our little handy table. What we want to do is count the number of groups that we have for this compound. So the number of groups is going to be equal to the number of bonds, number of single bonds, plus number of double bonds, double, not duple, plus the number of triple, plus the number of lone pairs. Add all those up. In our compound, we have 4 single bonds, no doubles, no triples, and no lone pairs is 4. That means we have 4 groups around the central atom in methane. So if you see our table right under my face here, the left-hand column is number of groups, and so ours has 4, so we're in the 3rd row. That 4 is obtained by having 4 bonds and 0 lone pairs, so that's the top line of that row. That means the bond angles for our molecule are going to be 109.5 degrees, and the shape is going to be tetrahedral. The hybridization is going to be sp3, and you can see right there the example that I give in the table is methane anyway. So start off with an easy one. We're going to start off with we're going to do an additional one now, number 2, which is going to be nitrogen tribromide, NBr3. Okay, so first thing we need to do is go back to our periodic table. I'm going to delete my marks from before. Remember that the number of valence electrons goes 1, 2, 3, 4, 5, 6, 7, 8. Nitrogen is 5, and bromine, because it's in group 17, has 7 valence electrons. So that's going to be equal to 5 valence electrons from the nitrogen plus 7 from the bromine times 3, because we have 3 bromines in the structure. That gives us a total of 26 valence electrons. So these are the electrons that we can work with when we're building our structure. Now we draw our compound out. We put nitrogen in the center because it's the first one listed. Like that. And if you look at the number of single bonds we had to draw to connect it, we have 3 single bonds. Each single bond is 2 electrons, which is 6 electrons we just spent. So if you take our total, which was 26 valence electrons from the first step, subtract the 6 that we used to make our single bonds, that leaves us with 20. Our next step is what we want to do is use these additional valence electrons, these 20 valence electrons, and use them to fill the octets of all of the outer atoms. So the bromines here are the outer atoms. Those bromines currently each only have 2 electrons, which are the 2 electrons associated with a single bond. So what we need to do is add 6 electrons for each bromine, and we add these in pairs. So we can add 1 pair, 2 pairs, 3 pairs on that bromine atom. That gives it a total of now 8 valence electrons. We do the same for the other bromines. We want to fill up all of their octets. And there. So what we've done is we've added 6 to each bromine. There's 3 bromines, so we've just added 18 valence electrons. So we subtract that from our total, and we're left with 2. So we still have 2 valence electrons, and so what we do if we have any leftover valence electrons at this step, those leftovers go on the central atom. So let's put those on the nitrogen. That gets rid of our final 2, and now we've spent all of our electrons. Okay. So the next step that we can do here is to do our formal charges. The nitrogen has 5 valence electrons, as we found before. It is making 3 bonds. So you subtract 3. It has 2 unshared electrons on it, which are the lone pair here. So you subtract 2 and you get 0. So there's no formal charge on the nitrogen. If there is no formal charge on an atom, you don't draw anything. If there's a positive, you put a plus. If there's a negative formal charge, you put a negative sign. Now for the bromine, it has 7 valence electrons. Subtract 1 for the only single bond that it has. And we need to subtract 6 for the 6 electrons in the lone pairs. That gives us a total of 0. So again, we're good. This structure is fine, just fine the way it is written. I guess the next thing we would like to do is count the number of groups around the central atom. We have 3 single bonds. We have 0 double bonds, 0 triple bonds, and we have 1 lone pair equals 4. So we have 4 groups again, in this case, which is made by 3 bonds, 1 lone pair. So what we can do is look at our table that you can see right below me to the left of the screen. We want to go to 4 groups. We want to go to 3 bonds and 1 lone pair. That gives us bond angles of 109.5. And the structure you can see there is trigonal pyramidal. The hybridization on the nitrogen is sp3. Great. Easy peasy, right? Okay, so the next example we would like to do, they're getting slightly more complex with each example, is going to be formaldehyde. Formaldehyde has the structure CH2O, and we need to find out how many valence electrons we have total as our first step. Okay, so we have 2 hydrogens, which is 1 valence electron each. We have a carbon, which is 4 valence electrons, and we have an oxygen, which is 6. Remember, it goes 1, 2, 3, 4, 5, 6, 7, 8. So we have 1, 4, and 6. So our formaldehyde valence electrons is going to be equal to 4 for the carbon, plus 1 for the hydrogen times 2, because we have 2 of them, plus 6 for the oxygen, gives us a total of 12, if my math is correct. Now we want to draw the structure out with the central atom in the middle. Central atom is the first one drawn, first one listed, which is the carbon. So we're going to put an oxygen here, a hydrogen here, and a hydrogen here. So we've just drawn 3 single bonds. So 3 bonds times 2 electrons per bond is 6 electrons we've already spent by drawing those single bonds. We subtract that from our total. 12 valence electrons minus 6 leaves us with 6 remaining electrons. With those electrons, we want to fill up the outer shells of the outer elements in the structure. So hydrogen already is full in both of our hydrogens because it only needs 2 electrons. It has 2 electrons in each atom. The oxygen needs more though. It's in the second row, it needs an octet. So we're going to add lone pairs. 1, 2, 3 lone pairs to give it an octet. And we do that because it now has 8 electrons. 4 in the lone pairs and 1 in the single bond to the carbon. Now our next step is we want to check all of our atoms to see that they have a full octet, or a full outer shell I should say, because hydrogens don't make an octet. The hydrogens are okay already as we indicated. The oxygen is okay now that we gave it those extra electrons, but the carbon does not have a full octet. The carbon has 3 single bonds coming from it. Those 3 single bonds are 2 electrons each, so the carbon at the moment only has 6 valence electrons. Okay, so that means if possible, we would like to look at adjacent atoms that have lone pairs and use one of those electron pairs to make it a double bond. So we can certainly do that. Why don't we look at an atom adjacent to the carbon that has a lone pair? Oxygen is the only possibility here. So if we look at one of those lone pairs, what we want to do is drag it down, and we're going to draw our new structure, which is now going to look like this. Carbon double bond oxygen. We only have 2 lone pairs left on the oxygen because we used one to make that second bond. Now the hydrogens still have full outer shells, still have 2 valence electrons each. The oxygen still has a full octet because it has 4 electrons now in the bond, 2 times 2, plus 4 electrons that are unshared, the 2 lone pairs. Carbon now, it has 4 bonds going to it. It has 2 going to oxygen, 1 going to hydrogen, 1 going to hydrogen. 4 bonds times 2 electrons is 8, so now the carbon has its octet as well. So it's quite happy. Next up, check our formal charges. First, hydrogen has 1 valence electron minus 1 bond minus 0 unshared electrons is 0. Carbon has 4 valence electrons minus 4 bonds that it's currently making. Double bond counts as 2. Minus 0, there's no lone pairs around that carbon, gives us a formal charge of 0. And now the oxygen, normally an oxygen atom off the periodic table has 6 valence electrons. It's making 2 bonds to carbon, a double bond, so we subtract 2. And now we must subtract 4 for the 4 electrons that are unshared, the 2 lone pairs, and that leaves us with 0. So all of these atoms have formal charges of 0. That's the ideal situation. Okay. Next example. We're going to do an example now of a molecule called acetamide. Okay, and acetamide has the structure CH3 CONH2. Now this is a bit more of a complex structure because this one actually has 3 central atoms. And in cases where the conductivity is a little bit more complex than the examples we've seen so far, I'm not going to make you guess as to what the conductivity looks like. I'll let you know. So in this particular molecule, we have a carbon bonded to a hydrogen, hydrogen, hydrogen. That's the CH3 part. It's connected to a carbon. That carbon is connected to an oxygen and a nitrogen. And the nitrogen has 2 hydrogens coming from it as well. Looks like that. So we need to count up all our valence electrons. We have C2, we have H, what do we have? 1, 2, 3, 4, 5, N, and O. So we got a lot of elements to deal with here. Go back to our periodic table. We have C, which is 4, H, which is 1, N, which is 5, oxygen, which is 6. So we have carbon is 4 times 2, plus for hydrogen we have 5 times 1. I should do it the other way around. 1 times 5 hydrogens, plus nitrogen has 5 electrons, plus 6 for the oxygen, equals a total of 8 plus 18, 24. If you look at our structure, we have already drawn 1, 2, 3, 4, 5, 6, 7, 8 single bonds. 8 single bonds is equal to 16 electrons. We subtract that from above, and we get a total of 8 valence electrons. We want to use this to fill up the octets of outer atoms, and the hydrogens are already filled, so we don't have to worry about the hydrogens. We have to worry about the nitrogen and the oxygen. So let's fill the oxygen first. To fill its octet, it needs 6 electrons, because it already has 2. So that's used 6 electrons of our 8. Leaves us with 2. Those 2 electrons go in the next outer atom, which is nitrogen. That fills nitrogen's octet. Leaves us with 0. So we are out of electrons. We can't add any more to the structure. That's all we have to play with. And what we can do though is check all of our atoms to make sure they have full octets. All the hydrogens are happy. The oxygen is happy. It has 8. The nitrogen is happy. It has 8. The one that's problematic is the carbon in the center, because it only is making 3 single bonds, which each has 2 electrons, which is 6 valence electrons. So it does not have a full octet. So we need to make a double bond to give it a full octet. The issue that we have in this particular molecule is that there's 2 ways that we could achieve that. Remember, what we want to do is find an adjacent atom with a lone pair and bring the electrons down from the lone pair to make a double bond. So oxygen, we could use one of the pairs from oxygen, or we could use one of the pairs from the nitrogen. So we have a choice to make. And so let's draw out both possibilities. There's that one, or there's that one. So what do we get in these 2 cases? Well, let's say we do the oxygen one. That choice would look like this. Carbon, hydrogen, hydrogen, carbon, double bond oxygen, 2 lone pairs left, nitrogen, hydrogen, hydrogen, nitrogen, like that. So that's one possibility. The other possibility is if the lone pair came from the nitrogen instead. That would give us option, I'm going to call this option A and option B. Now we would have a multiple bond between the carbon and the nitrogen. The lone pair is gone because we used that lone pair and the nitrogen to make the multiple bond. And now we add our hydrogens. So at this point, how do we decide which of these two structures is better, A or B? Well, what we do is our next step is assigning formal charges. We're going to use formal charges to decide which structure is best. So if you start on the left-hand structure, all of the hydrogens will have formal charges of 0, because all of the hydrogens will be one valence electron minus one bond minus 0 unshared electrons is 0. This carbon, 4 valence electrons from carbon off the periodic table, minus 4 bonds, minus 0 equals 0. So there's no formal charge on that carbon. The oxygen has 6 valence electrons, remember, minus 2 for the double bond, 2 bonds, minus 4 electrons for the 2 lone pairs is 0. So far everything's great. No formal charges. 0 formal charges is the best way to have it. Carbon, we have 4 valence electrons. We want to subtract 4 bonds, and we want to subtract 0 because there's no unshared electrons around the carbon. That's 0. Our nitrogen, finally, is 5 valence electrons. If you remember from way up here, we got 5 off the periodic table. We want to subtract 3 for the 3 bonds it's making, subtract 2 for the 2 electrons in the lone pair, equals 0 as well. This structure looks great. All of the atoms have a formal charge of 0, so this is likely going to be our winner, but just to prove it, let's check the other structure as well. This one is, okay, the carbon is still 0 here, that hasn't changed. This carbon in the center is still 4 minus 0 equals 0. So that is still formal charge of 0. But the oxygen has a formal charge of 6, which is the number of valence electrons in the oxygen. Subtract 1 for the single bond. Subtract 6 for the 6 electrons in lone pairs. That equals -1. So we have a negative formal charge on that carbon, which we're going to indicate in the structure by just putting a minus sign next to the oxygen like I did there. Next we got to do nitrogen. So nitrogen has 5 valence electrons minus 4 bonds minus 0 unshared electrons equals +1. So if it's got a +1 formal charge, we need to just put a positive on the nitrogen. So these two structures are both structures we could have drawn to make this structure correct to complete all the octets, but the preferred structure in this case has got to be structure A, because structure A leads to lower formal charges for all the elements that we're interested in here. All right. So sometimes you end up getting examples of molecules where when you draw the multiple possibilities, like we saw in the previous example, perhaps there's no difference in the structures that you draw. And I'm going to give an example of the nitrate anion. Nitrate anion is NO3-. Okay. Let's add up our valence electrons. Nitrogen gives us 5 plus 6 times 3 for the 3 oxygens plus 1. And that plus 1 comes from the fact that we have an anion, we have a -1 charge, so you have to add 1 electron for every 1 negative charge that you have. Subtract 1 for every positive charge that you have. So that gives us 6 times 3, 18, 19, 24 valence electrons. That's what we have to work with here. What we're going to do is draw out our structure now, nitrogen in the middle. Okay, we've just used up 6 electrons to draw those 3 single bonds to connect everything up, which leaves us with 18 valence electrons, which we're going to use to fill the outer octets, fill the octets of the outer atoms. So we're going to go 2, 4, 6, 8, 10, 12, 14, 16, 18. We've filled all the oxygens, we've used all 18, we're left with none to put on the central atom, so we're done with all of our electrons. Now we would do the check to make sure all of our atoms have full octets. All the outer oxygens certainly do, but the central nitrogen does not. If you look at it, it only has 3 single bonds. Each of those single bonds has 2 electrons, and that gives it a total of 6 valence electrons, so it needs another 2 electrons to have a full octet. All right, so what do we do if we need to make a full octet? Well, we look at adjacent atoms with lone pairs, and we bring one of those lone pairs down to make a double bond to help the central atom satisfy its octet. Great. Now, if you look at the nitrate structure, it has 3 atoms that are adjacent to the nitrogen that all have lone pairs. So you could remove that one, you could pull that one down, or you could pull one of those 3 pairs down. So we have 3 possible options in the 3 structures we're going to get. We're either going to get this one, 2 left on that oxygen, and 3 pairs here, and 3 pairs here. Or if you take one off the top top oxygen, you're going to have this structure. Or you take it from the rightmost oxygen and you have this structure. The next step is for all 3 of these, we would do like we did in the last example and try to use formal charges to figure out which is the best structure. I'm going to do this really quick because hopefully by now you guys know how to do formal charges. But the oxygens in this and this will have -1, the nitrogen +1. The middle structure, the nitrogen is +1, and the 2 lower oxygens are -1, -1. In the right-hand structure, we have +1, -1, and -1. We can't use formal charges in this example to say one is better than the other 2, because all 3 of these structures have 2 negatives and a positive. 2 negatives on oxygens and a positive on a nitrogen. So what we would do in this example is say that these 3 are equivalent contributors, they're of equivalent energy, and we call these resonance structures or resonance forms. And we connect them with one of these double-headed arrows. As you will learn in organic chemistry, arrows are very important, and it's very important you use the right kind. This particular arrow means resonance, not to be confused with this arrow, which means equilibrium. And what we would actually say in this molecule is that the true structure of the nitrate anion is an equal average of those 3 structures. So each nitrogen-oxygen bond would be about, say, 1 1/3 bond order. So it's like not quite a single bond, not quite a double bond, but instead somewhere in between. Resonance structures are quite important. Let's get even weirder. Okay, let's look at some examples that have exceptions to the octet rule. And this is an example I remember when I was in my undergrad struggling over. But if you follow the rules and follow the steps, it's actually a very straightforward example. And this example is going to be ClO2. Okay. This is an important molecule in atmospheric chemistry. It's important for degradation of ozone. We're going to add up the valence electrons here. And we're going to look at Cl, which is here, which has 7 valence electrons. Oxygen, which is here, has 6. So we're going to have 7 valence electrons for the chlorine plus 6 for the oxygen times 2. That gives us 19. So this is weird already because this is the first example we've seen where we have a number of electrons that's an odd number. Usually we like to put electrons down in pairs, either as bonds or as lone pairs. So we're going to be in a funny situation here. All right, chlorine goes in the center. We go to 1 oxygen on the left, 1 oxygen on the right. That's Cl, not carbon. We've just used 4 valence electrons to make those bonds, leaving us with 15. Fill up the outer octets, 2, 4, 6, 8, 10, 12. And that leaves us with 3 valence electrons. 3 valence electrons doesn't allow us to neatly put down pairs, but let's put 1 pair, which leaves us with 1 electron. And that last electron will also go on the central atom, and we'll just put it by itself down there. So this is a bit of an odd structure now because we have the chlorine with an odd electron out. You know, it doesn't have a complete set of pairs, but that's okay. It's not going to be a very stable molecule perhaps, but it's still a real molecule that does exist. Next step, what we want to do is check to make sure all of our outer atoms have a full octet, or all of our atoms have a full octet. The oxygens certainly do. The oxygens are fine. They each have 8 electrons, 1 bond and 3 pairs. The central chlorine, though, it's got 2 electrons in each bond for 4, right? So it's got 2 and 2 and 2 for that pair and 1 for a total of 7. So it does not have a full octet. So normally what we like to do is make multiple bonds by bringing down lone pairs on adjacent atoms. But if we do that with chlorine, we're going to go over the octet. We're going to exceed the octet. So exceeded octets are an exception to the octet rule that are only okay for central atoms in row 3 or lower. Let's go back to our periodic table. Okay, this is row 1. This is row 1. This is row 2. In organic chemistry, we hang out most often in row 2 because carbon, oxygen, nitrogen are there. This is row 3, so if the atom is in row 3 or lower, it's okay to exceed the octet, and chlorine is in that row. Okay, so that's what we're going to do then, I guess. What we can do first, though, if we want, is look at our... Get out of there now. What we're going to do is look at our formal charges that we're at the moment, where we're currently sitting. Oxygens, each oxygen has 6 valence electrons minus 1 bond minus 6 unshared electrons is -1. Same is true for the other oxygen, so it's minus, minus, and the chlorine is, I'm going to remove that so we don't mistake it. It has 7 valence electrons. Chlorine in the periodic table has 7. Subtract 2 for the 2 bonds, subtract 3 for the 3 unshared electrons, and that equals +2. So formal charges of greater than +1 or less than -1, so if there's +2, +3, +4, almost certainly you have the wrong structure. You're not at the correct number because those sorts of high formal charges are really, really disfavored. So we said we can make multiple bonds. We said that would help the chlorine get a full octet, and we said that's only okay in this example because chlorine is in row 3. So we can take one down from its neighbor, and if we do that, we get this structure. We get oxygen pair, pair, double bond, chlorine, lone pair is still there, single electron is still there, the oxygen on the other side is the same as before. So this structure might look a little bit better. Let's look at formal charges now. This oxygen is 6 minus 2 minus 4 is 0. So it's good. The chlorine now is 7 valence electrons minus 3 for the bonds, minus 3 for the electrons is plus 1. And the oxygen on the end, same as above, 6 valence electrons minus 1 bond minus 6 unshared electrons is negative 1. So we have a negative on the oxygen and a positive on the chlorine. What we can do in this case is make one additional multiple bond by taking the lone pair of electrons down. Then we get Cl, double bond to that oxygen, double bond to that oxygen, 2 lone pairs on each oxygen because we used one of the original 3 lone pairs to make the multiple bonds. We have the pair on the chlorine and a single electron on the chlorine. So we've gone way over the octet on this chlorine, right? If you look at the valence electrons that are currently around that chlorine atom, right? We've got 4 times 2 for the 4 single bond, or for the 2 double bonds, or the 4 bonds that it's making, plus 2 electrons for the lone pair, plus 1 electron for the single one. That gives us a total of 11. So this is way over, the octet. But that's okay. Chlorine's in row 3. We're not going to worry about it. We like this structure because now all the formal charges are 0. That's a great structure to have. Okay, so that was an example where it was kind of a 2-for-1. We had an odd number of electrons, which is one exception to the octet rule. We also had an exceeded octet that we see on that chlorine. Let's do another one where we have a compound that has less than a full octet. So the molecule I want to look at is going to be a simple one. It's going to be Bh3. And that will have a structure with boron in the center. And what happens is if we go over here on the periodic table, let's delete our crap from last time. Boron sits right there. It has 3 valence electrons. Hydrogen is still over here with 1 valence electron. After a while, you will stop consulting the periodic table. This will become second nature. Remember where they are. Okay, so we have 3 valence electrons for the boron, plus we have 1 times 3 valence electrons for the 3 hydrogens equals a total of 6 valence electrons. If you look down here in our structure, we've already drawn 3 single bonds, which is 6 electrons already. So we have 0 valence electrons remaining. We've got nothing more to add. The hydrogens are all okay. They have their outer shell filled, but the boron only has 6 valence electrons around it at the moment. It's got 3 single bonds times 2 electrons each. It only has 6 valence electrons. So it has less than an octet. So this is an exception to the octet rule. Boron, if you remember where it is on the periodic table, it's in row 2. Row 2 cannot exceed an octet. But it can have less. Or I guess fewer. Can have fewer than 8 electrons. It can have 7, it can have 6, as we'll see. So that's okay. So this boron, even though it has 6 valence electrons, does not have a full octet, but that's still okay. You can finish it off by looking at formal charges. The hydrogens, I don't think hydrogens ever have a formal charge when they're part of a compound except for 0. The boron has 3 valence electrons that we get from its position on the periodic table. Subtract 3 bonds, subtract 0 lone pairs equals 0 valence electrons. Great. I'll do an interesting variation of that one, actually. There's another compound I'd like to look at called Bf3. Boron compounds, as you'll see, often have less than a full octet. Actually, one thing before I leave the BH3 is we've been kind of ignoring this table underneath my face here. If you look at that boron in this structure, it is making 3 bonds that are single, plus 0 double, plus 0 triple, plus 0 lone pairs is 3 groups. So from our table, you can see 3 groups with 3 bonds means it's in the second sort of set there. It's the first row of the second group in our table. It's got a bond angle of 120 degrees. It will have a geometry that's trigonal planar and a hybridization on the boron that's sp2. Bf3, let's go back to this. We have B, F, F, F. We have 3 valence electrons for the boron, plus 7 for the fluorine times 3. That equals 24. 7 times 3 is 21, 24. Minus 6 electrons gives us 18 for what's left. So what we need to do now with our Bf3 is add electrons to fill up the outer atom octets. Fluorine wants 2, 4, 6, 8, 10, 12, 14, 16, 18. We've added 18 electrons. We subtract that from our total, leaving 0. There's no more left behind to put on the central atom. Boron, as the central atom here, doesn't have a full octet. We know that's commonly the case with boron, so we're not too worried about that at this point. But there are atoms attached to the boron that can give, that we could bring down to make a double bond to the boron if we wanted to. So for example, what we could do if we felt like it is if we took a pair of electrons from a fluorine and brought it down, you could create a structure that looks like this. Okay, each of the fluorines still has some lone pairs around them. This guy only has 2 lone pairs because we used one to make the multiple bond. And we could have done this with any of the 3 fluorines to make resonance structures. However, we normally don't do this with boron. And I'll show you why. If we go back to our original structure, I'm going to erase the red there, and we're going to do formal charges. That fluorine has 7 valence electrons off the periodic table, minus 1 bond, minus 6 electrons in lone pairs is 0. So all of the fluorines are 0. The boron has 3 valence electrons, minus 3 bonds, minus 0 electrons that are unshared is 0. So the boron is 0 too. Everything's 0. Formal charges are great for that compound. Even though the boron doesn't have a full octet, formal charges are great. Compound down here, however, has 0 for the fluorine, 0 for the fluorine. The boron is now 3 valence electrons minus 4 bonds minus 0 is negative 1. So put a negative on the boron. The fluorine becomes 7 minus 2 for the 2 bonds minus 4 for the 4 electrons is plus 1. So if we make a double bond between the fluorine and the boron, we have to put a positive charge on the fluorine and boron gets a negative charge. So in terms of formal charges, this is not great. In fact, fluorine is the most electronegative atom on the whole periodic table. That's because out of the atoms that forms bonds, it's at the top right corner of the periodic table. Helium we kind of ignore because helium typically doesn't bond. It's a noble gas. Formal charges that are positive are very disfavored on atoms that are very electronegative. So we don't really like having fluorine here with a positive charge. Okay, so this is not what we want. Boron also, it's sort of on the left side of the p block. It's not very electronegative at all. It's fairly electropositive. It doesn't necessarily want a negative formal charge either. So overall, we would say this structure is not very good. We would prefer the one up here based on the formal charge argument. And this is sort of a unique thing that you see with boron. You see it with beryllium too, although beryllium doesn't appear too often in organic chemistry. Let's do one more example. This video is starting to get long. And this one is going to be ICl4. Okay. Periodic table, we have I and Cl both in the same row, both 7 valence electrons each. So we have 7 for the iodine plus 7 for the chlorine times 4. And that gives us what? 35? Okay. Actually, I made a mistake. It's not ICl4, it's ICl4 minus. That's the actual ion that we're dealing with. So we have to add 1 for the negative charge. Gives us 36. Great. I's in the middle. We started with 36. We subtract 8 for those 4 single bonds. That leaves us with 28. Fill up the outer octets. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. And we've filled up all the outer octets. Minus 24 gives us 4 valence electrons. Any leftover valence electrons at this point we have to put on the central atom, which we might be uncomfortable doing, given that iodine in the middle there already has its full octet. However, we have these electrons, they got to go somewhere, and it's okay for iodine to exceed its octet. We're going to put 2 pairs. And the reason why we can go over 8 for iodine is because it's in the 3rd row, right? This is the 3rd row, or below. Of course, it's in the 5th row. So yeah, I can totally take those extra electrons there. Okay, we don't need, every atom has a full octet and then some, so we don't need to make any multiple bonds here to figure out, to fill up any octets. Everything's got a full octet. Let's do the formal charge thing. Chlorine has 7 off the periodic table, minus 1 for the single bond, minus 6 for the 3 lone pairs is 0. So all the chlorines have charges of 0. And I'm drawing them in here just to be explicit. Normally you don't draw anything if the formal charge is 0. In fact, I'm going to get rid of those because I don't want people to start drawing zeros if there's 0 formal charge. Okay, iodine in the center. Iodine is also 7. Notice that it has 4 single bonds coming to it, minus 4 electrons in the 2 lone pairs is negative 1. So that iodine, we want to somewhere stick a negative sign. Okay. Some people like to draw a circle around it. That's fine too if you like to do that. What I'm going to caution you against doing though is drawing your lone pairs any other way than the way I've drawn them here. So what some people might like to draw for Cl, instead of drawing the lone pairs, they'll draw like lines like this. Don't do that. Bad. So draw them just the way I have them before. So in this case, iodine has a formal charge of minus 1. All the other atoms have formal charges of 0. We've exceeded the octet on the iodine, but hey, it's no big deal because it's 3rd row or below. If you were to calculate here the number of groups, you would say the iodine has 4 single bonds plus 1 double bond, sorry, 0 double bonds, plus 0 triple bonds, plus 2 lone pairs, for a total of 6. So we go to our trusty table that you see under me here. 6, we would want to look at the bottom row where it's 4 bonds and 2 lone pairs. That means we have bond angles of 90 degrees. The shape is what we would call square planar. And the example there is xenon tetrafluoride, but ICl4- is the same thing. What that shape would look like, and the way we would sometimes draw this, is the iodine is here, and we sometimes use these hashed and wedged bonds to indicate the 3D shape of a molecule, where the ones that are solid wedged coming out means it's sticking out in front, like towards us, out of the plane of the paper, and the hashed bonds you see in back are going backwards away from us. And this would make a flat molecule where that's a right angle, that's a right angle, that's a right angle, that's a right angle. And we have to have our other atoms, which I believe are chlorines. Great. And plus, then above it, it would have kind of a lone pair, and below it, you can draw it like that if you want. But if you look at the actual atoms, they form kind of a square shape, and it's flat, and that's where we get the name of the shape, square planar. All right, I'm going to do one more example. Why not? If you're still with me now, we don't mind doing one more. We're going to do a molecule called acetylene. Acetylene is C2H2. This has a structure that looks like this, with hydrogen, carbon, carbon, hydrogen. So there's 2 central atoms here, the 2 carbons. So I'm going to give you the connectivity in this example. So valence electrons, we have 4 for carbon times 2, which is 8, plus 1 for hydrogen times 2, which is 2, which gives you 10. In our structure that we've already drawn right there, we already have 6 electrons that we've used to make 3 bonds. So we subtract 6 to leave 4 valence electrons. And what we want to do now is put them on the outer atoms to fill up octets. The outer atoms are the 2 hydrogens, they're full already. And we have 4 left that we can put on the 2 central atoms, which are the 2 carbons. So we can put 2 lone pairs in. Why don't we be even here and put a lone pair on each of the carbons, so that each are equal, each has the same number. We've used those 4 electrons up and are left with 0. All right, now this structure isn't fantastic because the carbons that are in the middle do not have full octets. They only have, if you count them up, 6 valence electrons each, not 8. So what we would want to do is make multiple bonds so that those carbons are able to make a full octet. So if you look at the left-hand carbon, we can make a multiple bond to him or her, don't know the gender. Grab a pair of electrons, bring them down here, and we're left with hydrogen, carbon, lone pair there, double bond, carbon, hydrogen. So that lone pair is gone because we use it to make a multiple bond. And that is great for the carbon on the left because it now has a full octet. Carbon on the right's not doing so good though. If you look at the valence electrons, this has 8, 3 in the bonds times 2 plus the lone pair, but the carbon on the right only has 6. So if it doesn't have a full octet, again you do the same thing. Look for an adjacent atom with a lone pair. There is one. You can bring it down as well, and that would give us a triple bond. Great. All the atoms have full outer shells, full octets for the carbons. Our formal charges for each carbon is 4 minus 4 bonds minus 0 is 0. Everything is happy and stable and even, and we ended up with a molecule with a triple bond in it, which is the first in this example. For each carbon, if we want to count the number of groups, right, the number of groups for that carbon, for either carbon, is going to be equal to I'm back. Someone came to the door. Election season. Okay, number of groups are, in this case, carbon, we have 1 single bond, 0 double bonds. We have 1 triple bond, and 0 lone pairs is 2 groups. Look on our table. 2 groups means 2 bonding groups, 0 lone pairs. The bond angle will be 180 degrees. And the hybridization on that carbon is going to be sp. Same with this carbon, it's sp. We'd say the shape of each of those central atoms is linear. And what you'll find is you can make more complex molecules with multiple central atoms where the geometry of each central atom can be different. So you can have a molecule that looks, say, like this. Hydrogen, 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 carbon, oxygen, nitrogen, hydrogen. Let's keep going. Let's go carbon, hydrogen, hydrogen, carbon, bond, 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 carbon, hydrogen. So here's a molecule where we have multiple atoms, multiple central atoms, and this would still be considered a small organic molecule. And we can have different hybridizations on multiple atoms. So that carbon has 4 groups. If you look at the table, it's got 4 bonding groups, 0 lone pairs. So that means it's going to have bond angles of 109.5. They're all going to be that's going to be tetrahedral. And the hybridization of that carbon is sp3. This next one, it has 3 bonding groups, 2 singles and a double. So single, single, double counts as 3 groups. That means it's going to be trigonal planar. And the hybridization is sp2. This carbon is also sp3 and tetrahedral. That carbon is sp and linear, okay, with bond angles of 180 degrees. So here we have multiple types of atoms in a single molecule with a wide variety of different bonding structures. Okay, that's it for me. That's our quick tutorial on how to draw Lewis structures. Practice as much as you can. Get good at this, get fast at it, and it only gets easier with practice. Bye-bye.